Hi everyone, thanks for tuning in. This is Nate, a Murph synthetic voice, talking to you from Gradient N. In this video we set up and train a voice classification neural net using the audio MNIST dataset, downloaded from Kaggle. The link and reference are in the description box below. The audio MNIST dataset contains samples of spoken digits 0 to 9 from 60 different speakers. We'll start with the fully connected audio MNIST net we built for our previous video, titled MNIST Audio Classification with a fully connected neural net. For the fully connected net, we renamed the sound files so that NetDesigner could parse their names for data labels. We also used only the data for the first 10 speakers in the dataset. The fully connected net has a sound input layer, 2 hidden layers, and output nodes connected to the sound files for digits 1, 2, 3, and so on. We're going to add an FFT, a Fast Fourier Transform, and a convolution to the fully connected net. First, we'll move the input layer to the left. Then we'll move the fully connected net to the right. We'll delete the connections between the input layer and the fully connected net. Then we'll place a process node and a convolutional layer. And connect it all together. We'll set up the FFT by selecting the process node we just inserted, and then bringing out the process editor. We'll set the FFT size to 128, the FFT data stride to 32, and the downconvert rate to 16. For our convolution, we'll leave the input size at 4 FFTs, and the input stride at 4. We'll set the input frame size to 8. A frame size of 8 will mean that we will be feeding our fully connected output net 2 convolutions per training step. Finally, we'll leave the output convolution size at 2, giving us a 2-to-1 reduction through the convolution. When we add an FFT to our net, we'll be sweeping the FFT across our waveforms and feeding its outputs to the convolution. We can set our FFT size. And we can also set our FFT stride, the increment we use to step the FFT across the waveform data. We can also set our convolutional size. In this case, our convolution is set to take 4 FFTs at a time. We can also set the stride for the convolution. Like the FFT stride, the convolution stride sets how far we move the convolution over the data for each training step. The audio MNIST waveforms have a sample rate of 48,000 Hz. Using a downsample rate of 16 gives us an FFT sample rate of 3,000 Hz. We can calculate FFT frequency step size by dividing downsample rate by FFT size. In our case, with an FFT size of 128, we have a step size of 23.4 Hz and a frequency range of 23.4 to 3,000 Hz. We'll change the activation functions for the hidden layers of our fully connected net from tanh to ReLU. And we'll leave the activation functions for the output nodes as sigmoid. We'll double-check that our validation files are still set up from the fully connected net we built our net from. Then we'll save the net. Naming it Audio MNIST FFT Conv. We'll bring out the training graph. And then start training. Training will take a while, and so we can fast forward through training a little, and then jump to the end. We stop training when it looks like the net has stabilized. Validation performance, in red, is no longer improving, and training performance, in blue, also appears to be fairly stable. The total training time is about 63 hours. We'll open our data output dialog window and save the net output data for some post-training analysis. Since we're going to be comparing the performance of our current net to the FFT net from our previous video, here's a quick reminder of the FFT net. The fully connected net in the FFT net used more nodes per layer and an additional layer compared to the fully connected net we're using with our current convolutional net. From the classification matrices, we see that training accuracy is 77.7% and validation accuracy is 66.3%. This is considerably better than for the FFT fully connected net from our previous video, which was 36.2% for training accuracy and 34.3% for validation accuracy. Considering that the net is time-based, that is, the FFT and convolution sweep across the waveforms, it's more helpful to look at time-based performance. We are showing graphically how the net performed. The top graph shows performance for our current net design, with an FFT, a convolution, and a fully connected net. The middle graph shows performance for the FFT plus fully connected net from our previous video. The stacked graphs show performance for each digit with a different color. The bottom graph shows the audio waveform for the corresponding digit. For file subject 0110.wave, we can clearly see the performance difference between the two nets. The previous net performs reasonably well identifying digit 1 in blue in localized regions, but the current net with the convolution performs well over the entire waveform. For digit 2 in orange, we can again see that the current convolutional net outperforms the previous FFT plus fully connected net. For digit 3 in gray, we can see that the current net outperforms the previous net in the voiced region of the waveform. However, both nets still struggle in the unvoiced region, especially during the TH sound, where the net strongly indicates 6 in green. 4 in yellow is identified clearly in the voiced region for both nets. 5 in light blue is identified better with the current net with the convolution. For 6 in green, the current net identifies the voiced portion and the X sound of the waveform better, but actually performs slightly worse at the start of the S sound at the beginning of the waveform. The current net performs better for digit 7 in dark blue across the full waveform. Again, the current net performs better for 8 in burnt orange across the waveform. The current net with the convolution also performs better for 9 in gray. 0 in brown is identified clearly by the current net. Now we will look at a few validation samples. For subject 9, digit 1 is clearly identified. Likewise, the validation sample for subject 9, digit 3 is clearly identified. Digit 4 performance is also good. Similar to the training performance for subject 1, the validation performance for subject 9, digit 6, has a little more ambiguity. For digit 8, validation performance is pretty good over the non-silent regions of the waveform. By adding a convolutional net following the FFT, the net is able to learn and recognize patterns in FFT sequences, giving the fully connected net unique keys to learn for each digit. In our net, the convolution is learning patterns in 8 sequential FFTs. By sweeping the convolution across waveform time, it can learn the phonemes and unvoiced parts of the MNIST numbers. When we set up our convolution to feed the fully connected net, the fully connected net learns from the convolution but also teaches it through backpropagation the patterns it needs to meet its training requirements. Thanks for watching, we'll see you next time.